So the topic on numerical differentiation integration assumes that you have already done interpolation. So the methods of carrying out numerical integration and differentiation will be derived based on your concepts on interpolation. So we start by the first numerical differentiation. So a numerical differentiation is simply the process of calculating the value of a derivative when the value of the function are given in tabular form. So this is the process of calculating the value of the derivative of a function y equals to f of x at some assigned values of x from a given values of x and y for the function. So I refer them as xi, yi. So if we have values of a function, you may not necessarily know the function explicitly, but you have the table values of x and y for the function. Then you're asked to find the derivative of that particular function for a given point x. So what will help you to carry out the derivative of that function at that particular point is this process we are calling numerical differentiation. And it's very applicable when maybe the function we are dealing with is very complicated to differentiate by the non-analytic methods we learned in calculus course, or the function is not given explicitly, only the values of the function at x and y are specified. So in such cases, the process of numerical differentiation will be useful to allow you compute the derivative. Is anyone having a problem on joining? Let me know. Class rep, is there anyone who has an issue on joining the class? Okay, good. So, to compute dy dx, we first replace the exact function or relation y equals to f of x by the best interpolating polynomial which we can call it phi of x, and then differentiate polynomial. So to calculate the derivative of a function, what we do, like what we are doing in the process of interpolation, we obtain the correct approximating polynomial. And then from this interpolating polynomial, we differentiate it to get the value of the derivative of the function up to the specified value of x. And from your earlier discussion, you discussed several methods of carrying out interpolation. And the methods of interpolation were broadly classified into two classes, where we have methods based on equally spaced mesh points, and we have methods based on unequally spaced mesh points. So depending on the problem you're solving, then it will guide you on which formula or which is a correct interpolating polynomial for you to apply. So if I may ask, what are some of the interpolating formulas that you discussed earlier on with your teacher? Example of any interpolating polynomial that you, interpolating formula that you earlier on discussed? Any example of interpolating formula that you remember?
Newton's backward formula.
Correct, Newton backward formula. Any other?
Newton's
Apart from
forward.
Newton backward?
Forward.
Yes, if you have backward, then you also have forward. So you have Newton forward formula. Any other? Any other interpolating formula that you remember? Apart from Newton backward and forward?
Lagrange.
Lagrange interpolation, correct? Any other?
Inverse.
Yes, there is inverse Lagrange interpolation when you are finding x given y. Any other? So when do we apply the Newton forward interpolation formula? When do you apply the Newton forward interpolation formula? For example, let me give you, this is just a by the way, recall. So the following are formulas interpolation formulas. So first, let's classify those based on equally spaced mesh points. So one, we have the Newton forward interpolation formula. So N, F, I, F. or sometimes people call it Newton's forward difference formula. So the term interpolation can be replaced by difference. So Newton's forward interpolation formula, number 2, we have Newton's backward interpolation formula. NBIF, or you can also call it Newton's backward difference formula. Then number 3, so remember to apply Newton's forward interpolation formula, then values at the beginning of the difference table. So to apply Newton's forward interpolation formula, if you recall what you did, you use it to approximate values which are near the beginning or the top of the difference table, while the Newton's backward interpolation formula will be applied when you are doing approximation for values at the bottom of the difference table. Then can you tell me the formula that you will apply when you are near the middle of the difference table? When you are near the middle of the difference table, which is the best approximation formula that you need to apply?
Central difference.
Come again? Come again?
At trial, central difference interpolation formula.
Yeah, we have what we call Starling's interpolation formula. There's also what we call Bessel's interpolation formula. There's also what we call the Ivrit's formula, which may also be applied here. So these two will be applied for equally spaced mesh points for values near the middle of the difference table. Please check the textbook that you are given or what I shared through the class step to see the structure of those formulas and how they applied. Then also what someone said, Lagrange interpolation formula can also be applied for equally spaced mesh points. So also Lagrange interpolation formula can still be used here. Also, there's what we call the Newton's divided difference formula. So do not confuse Newton's divided difference formula with Newton forward and Newton backward. They are totally different formulas. So check to see the structure. Then also, once these are the formulas that will apply for the case of equally spaced mesh points. And what we call equally spaced mesh points are values, for example, if this 0, then I have 0.2, I have 0.4, I have 0.6, I have 0.8, I have 1.0, 1.2, 1.4, etc. So these are an example of mesh points which are of values of x. We call this one x0, x1, x2, x3, x4, x5, x6, x7, etc. So in this case, x0, x1, x2 all the way up to x7 are equally spaced. Mesh points. Because the difference between any consecutive values of xi's is uniform. And in this case, it would be 0.2. So when you see that this difference here is 0.2, this is 0.2, this is 0.2, 0.2, 0.2, etc. So such case, we call them equally spaced mesh points. And for the case of equally spaced mesh points, from what you did, you remember that all of them can be defined with respect to the initial or the starting mesh points x0. For example, x1, if the spacing is given difference h, if this difference is h units, then x1 is the same as x0 plus h units. Then x2 will be x0 plus, to move from this point x0 to this point x2. I should add how many h values?
2.
2. So I'll have 2h. Then x3 will be x0 plus how many units from x0 to reach x3?
3.
3. So 3h. Then similarly, x4 from x0 will be x0 plus. The number of steps I need to move from this point to this point, x4.
4h.
4h, correct. So then we can also define x5 in a similar way. So 4h. So 4h. Then if I have xp with respect to x0, if you follow that trend, it will be x0 plus. If x1 is
PH.
x0 plus h,
PH.
x2 x0 plus 2h. So xp will be
PH.
XO plus PH.
pH, correct. So then, in general, for equally spaced mesh points, any value x, or which you can say xp, is given by x0 plus pH, where x0 is the initial point, mesh point, or the starting. And then h is the interval of differencing, or we call it mesh space. These are things you discussed earlier on when you are doing the interpolation formulas. So maybe briefly just to those part A, then part B, methods based on unequally spaced mesh point. unequally spaced mesh points. So here we use Lagrange interpolation. And Newton's divided difference formula. So it's good for you to check and then see how each of these formulas are applied, because we will set them. And what we call unequally spaced mesh points are, for example, if I have 0, 0.2, 0.3, 0.6, 0.9, say 1.4, 1.5, 1.9. So for example, these values are unequally spaced because the difference between consecutive values is not uniform. For instance, here difference is 0.2, here difference is 0.1, here is 0.3, here is 0.3, 0.5, 0.1, 0.4. You see, all these numbers are not the same. So such are examples of what we call the unequally spaced mesh points. So for the unequally spaced mesh points, it's not easy to express other values of x in terms of the initial, the starting values x naught, because of this varying distance between consecutive values. So back to our discussion on numerical differentiation. We say the choice of the interpolation formula to be used will depend on the assigned value of x at which the derivative is desired. So if the value of x the values of x are equally spaced, and equally spaced sometimes we can say equispaced. And the derivative is required near the beginning of the table then we employ Newton's forward formula. So just the same way when you are doing interpolation problem and you want to get the value near the beginning of the table, then you apply the Newton forward difference formula is the same thing. That if you want to find the dy dx near the beginning of the table, then your dy dx will be derived based on the Newton's forward interpolation formula. Then 2, if it is required, near the end of the table, then we use Newton backward formula. That's simply to say that the derivative formula that you'll apply if you are dealing with case of equally spaced mesh points, and you have been asked to find the derivative at the end of the table, then your method should be derived based from the Newton's backward interpolation formula. Then 3, if the values are near the middle of the difference table or the middle of the table, then we use which formula?
Stalin and Besson.
Yeah, we use either Stirling or Bessel's formula because those are the ones which are used to do the interpolation near the middle. So we use Stirling's or Bessel's formula. So that is the case of equal spaced mesh points. Then if the values of x are not equally spaced, so if the values of x are not equispaced, then we use Lagrange's formula or the Newton's divided difference formula. So I will demonstrate how we derive the differentiation, numerical differentiation formulas based on the Newton forward difference formula. And once we have discussed that, then you should be able to go and apply the same derivations for other different numerical differentiation formulas based on what you have earlier on discussed on different methods of carrying out interpolation. So derivation of numerical differentiation formula using Newton's forward interpolation formula. So consider the function y equals to f of x which is tabulated for equally spaced mesh points. So when we say this, then we mean any x value is given by x naught plus ph where h is the interval of differencing or mesh spacing, while x naught is the initial mesh point of the starting mesh point. So we know that the Newton forward interpolation formula is y, which is f of x, is given by f naught plus p forward of f naught plus p into p minus 1 over 2 factorial second forward of f naught plus p into p minus 1, p minus 2, then divided by 3 factorial third forward of f naught plus other several terms. I hope this is a familiar formula to you. Do you recall this? And please remember that when we say y equals to f of x, then f of xk can be written as f sub k or can be written as y sub k. So either maybe you can either use f or y to write the formula. So probably these f values can be changed to y. Maybe that is what you are what you are given by Dr. Jen. Did you use f or y when you are writing the formula for the Newton forward? When you check your book, why are you using f or why are you using y?
Y.
Y, yeah. So whether you use y or f, they exactly mean the same thing. So whether f or y, whether you use f or y, you'll be having the same thing. So whether you use f or you use y is exactly the same formula. But now, because you say that your teacher used y, for us to be consistent, let us take the same trend that you are used to, so that we don't confuse you. Plus other several terms. So we are saying that y is given by y naught plus p times forward of y naught plus p into p minus 1 over 2 factorial forward squared of y naught plus p into p minus 1, p minus 2 over 3 factorial third forward of y naught plus other several terms. Remember, our objective is to find the y dx. So from this equation, dy dp, remember y naught is the initial value of y at x naught, so it's a constant. So the derivative of a constant is 0. So when I differentiate this with respect to p, I just get 0. And then when I differentiate this term with respect to p, I'll have the derivative of this term with respect to p. Will be
0.
forward of y naught. Remember, forward of y naught, second forward of y naught, third forward of y naught, etc. Those are constant, they're numbers. If you remember when we were doing the difference table. So those are just constant values. So then to differentiate this part, simply when I open this bracket, I'll have p times p will give me p squared. Then minus p times 1 is p divided by 2 factorial. And 2 factorial just 2. So when you differentiate p squared with respect to p, you get
2p minus 1.
2p minus 1. Then divided by 2 factorial just the same as 2. So I'll have 2p minus 1 over 2, then second forward of y naught plus, then this other part, I'll have it the same as 2 p squared minus p for the first product, then I need to multiply by p minus 2. So p squared times p is p power 3. P squared times this will get minus 2p squared. And then this by this will give us minus p squared. And then minus p times minus 2 is plus 2p. Then what the value of 3 factorial?
6.
3 factorial is 6. So I'll have 6. Then when I differentiate p power 3, with respect to p,
I can see there are like terms there. Minus 2p
yeah,
squared.
so we can,
minus
yes, like terms. So we have p power 3, then minus 3p squared plus 2p, yes, correct. So when you differentiate the first term with respect to p,
3p squared.
3p squared, and then minus
6p.
6p, and then plus
2.
plus 2, correct. Then third forward of y naught. Then you can write the next term and do the same process, and you get the derivative, the next term followed by the next term. Because remember, this Newton forward interpolation formula is an infinite series. It's a formula having infinite terms. The stopping point depends on the table, the size of the table you have. So since x, any general value of x when they are equally spaced is x naught plus ph, then what is dx dp? Remember, x naught is the initial value is a constant, h is also a constant, the mesh spacing. So when I differentiate the right-hand side with respect to p, I'll get x equals to x naught plus ph, so dx dp is
H.
h, correct. So which means dp dx is if dx dp is h, what is the p dx?
1 over h.
1 over h, the reciprocal of the right-hand side, correct. So if you remember your calculus 1 work, if I want dy dx, I can write as dy dp times dp dx. This is by chain rule. So which means then our decided dy dx is the same as dy dp, which is given here, but then dp dx is 1 over h. So the same as 1 over h. So this thing is the same as 1 over h times dy dp. So 1 over h into the first term here is the forward of y naught plus 2p minus 1 over 2 second forward of y naught plus 3p squared minus 6p plus 2 divided by 6 third forward of y naught, then plus other several terms. So that is the formula. So this is what will give us the formula for working out the dy dx for any given value of x for equally spaced mesh points. But if x equals to x naught, then we know we are saying that x is the same as x naught plus ph. So when I replace x for x naught, so I'll have this, so that my p will be x equals to x naught, means p will be, when you evaluate this, so solve for p when x naught equals to x naught plus ph.
Is it 0?
0. because it's simply x naught minus x naught is 0. So 0 equals to pH. You divide through by h, you get 0. So this means that p will be equals to 0. So which means that this formula will now be dy dx at the point when x equals to x naught is the same as 1 over h into forward of y naught. Now, if I replace where there's p by 0, this coefficient will be for 2 times 0 minus 1 over 2 gives
minus 1 over 2.
minus 1 over 2. So minus a half second forward of y naught. Then can you do the same thing? Replace where there's p by 0 and tell me the coefficient of the third forward of y naught.
Done.
A third. So I'll have a third forward of y naught. Then I want you to do as an exercise. If you are to extend to write the fourth, fifth, sixth, the next 3 terms of this Newton forward interpolation formula, and you do the same process we've done for these first 4 terms, you will also get that the next term will be minus 1 over 4, the fourth forward of y naught. Next term will be plus 1 over 5, the fifth forward of y naught. Next term will be minus 1 over 6, the sixth forward of y naught. Next term will be 1 over 7, seventh forward of y naught, minus 1 over 8, eighth forward of y naught, plus other several terms. So the terms of this formula can be predicted, and it's very easy pattern to predict. If you are to write the next term of the Newton forward interpolation formula and you do the same process, you will find out that this would be the next terms. So this formula, what I want to put in green box. Let me call this one 1. So this formula 1 is what we use to find the first derivative of a function at a value of x near the beginning of the table when the values of x are equally spaced. Then this formula in blue, if I may call it 0, is exactly the same thing, but the main difference between 1 and this 0 is that 0 will be applied when you are being asked to find the value of the derivative near the beginning of the difference table for values of x which are not necessarily given in the table. For instance, if I have an arbitrary table, say this is x, these are y values, say 1.0, 1.2, 1.4, 1.6, 1.8, 2.0, say 2.2, say 2.4, and say 2.6. Let me say, for example, this is 9, 10, 11.3, 12.1, 16.5. These are just arbitrary numbers. They may not represent any meaningful function, but I'm just writing this one to demonstrate something. For example, if you are given this table and you are asked to find dy dx at x equals to 1, Then we use formula 1. Because the value x1 is at the beginning of the difference table and has the given value of y in the table itself. But if you are asked to find dy dx at 1.05, then we use formula 0. Because the number 1.05 cannot be read for this list of values of x. So then now we'll use this formula 0 by remembering that x is given by x0 plus ph. And in our case, if this is the table that is being given, what is the value of h? The spacing between values values of x following each other?
0.2.
0.2. So h will be 0.2. Then x0? Okay.
1.
1. So then now you say x is given by 1.05. So 1.05 equals to x0 is 1 plus p, which is unknown, times h, which is 0.2. So then you'll have 1.05 minus 1 equals to 0.2p. So this is 0.05 equals to 0.2p. Then we'll have p will be 0.05, then over 0.2. So this will give you a number, the value of p. So that value of p is what now you would be substituting in this formula 0 to get these coefficients of these forward differences. And you recall that these forward differences will be obtained from your table of forward differences. And then you'll be able now to replace each value correctly and then find the value of the dy dx. So when you are dealing with equally spaced mesh points, then you know that the formula to apply is either Newton forward, Newton backward, Darling or Bessel. And then if the values are near the beginning of the table, that means that the most appropriate formula is Newton forward. If they are near the middle, then Stirling or Bessel. If they are near the end, then Newton backward. In terms of the derivatives, you go through the same process we have done to derive this formula 0 to get a general formula for finding the derivative for any value of x near the beginning of the difference table. If it happens that the x we have been asked to find the derivative at is already given in the table, then you will use formula 1. But if the value of x is near the beginning of the table but is not among the given values in the table, then you'll be forced to apply formula 0. But in most cases, we'll give problems which whose derivatives are to be evaluated at values of x which are already given in the table of the function. So the most applicable formula will be formula 1. So if you differentiate formula 0, then you get the second derivative, because you know from your calculus that the derivative of the first derivative is the second derivative. And similarly, when you have the formula for the second derivative, when you differentiate the second derivative, you get the third derivative. And the same pattern can continue up to the point of finding the value of the nth derivative of a function. So I leave as an exercise for you to do to get the second derivative formula in this same case. So second derivative will be given by d squared y. Dx squared is 1 over h squared into second forward of y naught minus third forward of y naught plus 11. So this at x equals to x naught. That's to mean that you are finding the second derivative of a value of x already given in the table you are dealing with, over 12 fourth forward of y naught minus 1 minus 5 over 6 fifth forward of y naught plus 137 over 180 sixth forward of y naught minus other several terms. I'll give it as an exercise for you to actually show that these coefficients are the correct values when you are finding the second derivative. And the process is very easy. Have your Newton forward interpolation formula up to the term having the sixth forward derivative, sixth difference. Then differentiate that formula. And then once you differentiate it, you also differentiate it again to get the second derivative in terms of p. And then using chain rule, you'll see where we are getting this 1 over h squared. And then these terms, when you substitute p for 0, the coefficients will be the way we have written them here. There's no pattern to follow here. Like in the first derivative, where it's very easy to predict the next term, for the case of second derivative, it is not predictable. And then third derivative, so d cubed y dx cubed at x equals to x naught will be 1 over h cubed into the second of y naught minus 3 over 4. This should be third, not second. 3 over 4, 3 over 2, fourth forward of y naught, then plus other several terms. At your own free time, you can differentiate, have the many terms of the Newton forward interpolation formula to see how we can get this other terms of this same formula. But this is just a few terms after doing the derivation. So those are the formulas that we will make use of. Then when we will list without deriving, but the process is exactly the same. The differentiation formulas based on Newton backward interpolation formula. So Newton backward interpolation formula. Can you remind me the Newton backward interpolation formula that you are given? So recall Newton backward interpolation formula is y equals to
yn
yn
plus p
p, then
backward
backward
yn
then
plus p
into
bracket 1 plus p plus 1
p plus 1 over
2 factorial
2 factorial multiplied by
backward squared yn
backward squared yn, and then plus p into
p plus 1
p plus 1
p plus 2
p plus 2 over
3
3
factorial
factorial. Yeah,
backward
then
cubed.
yeah, then plus several terms. Okay. Yeah, you can see these are very good at class. So and remember, this formula is incomplete if you don't specify where x is given by x naught plus ph. Whenever you are writing the Newton forward and or Newton backward, or Stirling, Bessel, and Everett's formulas, always remember to give the relationship between any general value of x and the starting mesh point x naught. Because you see the formula is in terms of the variable p, yet our function is in terms of x. So you must always give a connection between the x and p. As usual, h is the interval of difference or the mesh spacing, and x naught is the starting mesh point. So if we go through exactly the same steps we have done in the previous derivation, we'll get this. The derivatives at x equals to x naught are, so I'm setting without deriving, but it's not a hard task for you to do. You can duplicate the same processes we did above to actually confirm the formulas we are going to list. So the first one, dy dx at x equals to x naught is given by 1 over h into backward yn plus a half backward squared yn plus a third backward cubed yn plus a quarter backward power 4 yn plus 1 over 5 backward power 5 yn plus 1 over 6 backward power 6 yn. In fact, this one is very easy in terms of predicting next term in the pattern, and you can write as many terms as you like. As you say, there's a correspondence between the denominators of the coefficients and the powers of the backward operator. And please, at one free time, do the same process we have done in the previous derivation to actually confirm that this is the correct structure of the formula. Then 2, the second derivative of y with respect to x at x equals to x naught, 1 over h squared into second squared yn, the backward operator, then backward cubed yn, then 11 over 12 backward power 4 yn plus 5 over 6 backward power 5 yn plus 137 over 180 backward power 6 yn. If you are keen enough, you can clearly see that this formula we are writing is more or less the same as what we have written in the Newton forward, but the only variation is that here the signs are all positives, yet signs in the Newton forward case Some were negative and some are positive. But here, all the signs are positive, but the size of the coefficients of each difference, exactly the same numbers. Then we can also list the formula for the third derivative. So 1 over h cubed into so these are the formulas we use to carry out a numerical differentiation. I've just written the two, one for Newton forward, another one for Newton backward, but I'm giving you powers to go and discuss the rest of the formulas based on the other interpolating formulas, say Lagrange interpolation and the Newton's divided difference formulas. And the trick is very easy. Once you know the interpolation formula, then just differentiate it. You'll get the derivative formula. So having that, then let's do an example that can help us understand how to apply these derivative formulas. So we provide two examples. One that will require us to apply the Newton backward formula of differentiation, and then the other one, Newton forward. So example, given that we have this table, these x values and y values. So 1.0, 7.989, 1.1, 8.403. Then we have 1.2, 8.781, and then 1.3, 9.129, 1.4, 9.451, 1.5, 9.750, then 1.6, 10.031. So given this table, the question is, find dy dx and d squared y dx squared at x equals to 1.1 and then b x equals to 1.6. Please write that question. So because of time, I'll share this But then when you have such a problem, the first thing is to draw a difference table. And then from the difference table, it will guide you on which formula you are going to apply. And the reason that we are saying that the first thing is to draw a difference table is because we can clearly say that these values of x are equally spaced. So when the values of x are equally spaced, then Newton forward or Newton backward or Stirling or Bessel formulas will be applied. And because of the equal distance between the consecutive values of x, then we require finite differences. So solution, first, we draw a difference table. So difference table will have the column for x and column for y. So this is x, then y. Then we have first difference, second difference, third, fourth, fifth, sixth, etc. So I'm just calling these columns first, second, etc. differences because I know from in the same table that I'll use to carry out both the forward and backward interpolation formulas. So I don't have to specify by either forward operator or the backward operator, because in any way, the way we get the differences is exactly the same. Lower number minus upper number. So the first number, the value of x is 1.0, 7.989. Then you skip a line, you go to 1.1, then 1.2, 1.3, 1.4, 1.5, then 1.6. So under 1.1, the y value is 8.403. 1.2 is 8.781. 1.3 is 9.129. 1.4 is 9.451. 1.5 is 9.750. 1.6 is 10.031. So you draw the values of x with their corresponding y values, skipping a space in between where the differences will be written. And when you find the difference here, lower minus upper number will give us what will be the value here?
0.414.
0.414, correct. So I have 0.414. Next. Zero point
378.
378, correct. So confirm these others, 0.348, 0.322, 0.299, then 0.281. Please, at your own free time, confirm this differences, because any mistake in them, in any one of them, will lead to error in the solution. So 0.030, 0.026, 0.023, minus 0.018, Then next here is 0.006, 0.004, 0.003, 0.005. Then we have minus 0.002, minus 0.001, 0.002. I hope you remember that when you are drawing a difference table, then the convention we take is usually you take the lower number minus the upper number. But that's how we are generating these values here. And then we have 0.001, 0.003, then here 0.002. So that's the first step, to draw the difference table. So the first part is to find the y dx at 1.1. So 1.1 is this number here. So this is where you have 1.1. So from the location of 1.1, do you apply Newton forward or Newton backward formula?
Forward.
Forward because it's near the beginning, correct? So once you have identified that, then have this line and pick this diagonal. So 1.1 is what now will be a x naught. And by default, this number, x naught, will be on the same line with y naught. So that is what we call your y naught. And this column, because it's the first difference column, then this will be forward of y naught. Then this will be second forward of y naught. This will be third forward of y naught, fourth forward of y naught, and then this will be fifth forward of y naught. So that is how you pick those values from your difference table. Therefore, you say y dx at x naught, x equals to x naught, by definition is 1 over h into first forward of y naught minus a half second forward of y naught plus a third forward of y naught minus a quarter fourth forward of y naught plus 1 over 5 fifth forward of y naught minus other several terms or plus other several terms. That is by definition. So in our case, dy dx at x equals to 1.1. So what is the value of h in this case?
(0.1).
0.1, the difference between the consecutive values of x. You see from 1.1 to 1 to 1.1 is 0.1, similar those other graphs. So h is 0.1. And then what is the forward of y naught from our table? The way we have identified that diagonal. So what do you replace for forward of y naught?
8.403.
Yeah, 0.378. This number here. Remember this, we are using this is y naught, not forward of y naught. So these differences are starting from here. So this is the number we are picking, forward of y naught. So the forward of y naught is given by 0.378 minus a half Then second forward of y naught from this table.
0.030.
Yeah, there's a minus here. So minus 0.030. Yeah. So minus 0.03. Then plus 1/3. If you check correctly, it will be 0.04. Then minus a quarter into minus 0.001. Then plus a fifth into 0.003. So we are stopping there because you see, after identifying your x naught, this line, and then picking this diagonal, we can only read up to the fifth difference. This number 0.02 is not along this diagonal. So the stopping point would be use of this number 0.003. So when you work out this, you will get something close to 3.952, nearest 3 decimal places. At your own free time, confirm that answer. Then there were two things for us to find the dy dx at 1.1 and also to find the second derivative at the same point. So the second derivative of y with respect to x at x equals to x naught, you recall we said the formula is 1/h² into second forward of y naught minus third forward of y naught plus 11/12 fourth forward of y naught, then minus 5/6 fifth forward of y naught, then plus other several terms. So ours is to find the d squared y, the x squared at x equals to 1.1. So what is the value of h? For the same
0.1.
problem? 0.1. So,
0.1.
yeah, so 1/0.1 square into, then in this table, what is the second forward of y naught?
Negative 0.030.
Correct. So remember, what you do is good to write this this diagonal when you're solving such a kind of problem, and then assign the values the correct differences so that when you start applying the formula, you just be doing direct substitution. So we'll have minus 0.030, then minus 0.04, then plus 11/12 into minus 0.01, then minus 5/6 into 0.003. So at your own free time, confirm that this will give approximately negative 3.74 as the solution for that second derivative. Now, part B is to find the derivatives at x equals to 1.6. So you'll go to your difference table, then identify the line where 1.6 is. So this is where you have 1.6. So once you have that, then pick the diagonal. So pick this diagonal. So with that, we'll have now, this is now what we call 1.6 now, because that's the reference point, will be your xn or x, then this will be your yn, then this becomes backward of yn, second backward of yn, third backward of yn, fourth backward of yn, fifth backward of yn, then sixth backward of yn. So you identify the diagonal and then label them appropriately. So the first is to write the formula. So b dy dx at x naught is 1 over h into backward yn plus a half backward squared yn plus a third backward cubed yn plus a quarter backward power 4yn plus a fifth backward power 5yn plus a sixth backward power 6yn plus several terms. But we know that we are going to stop at the backward power 6yn because our difference table can allow us to reach that as our maximum point we can read from the table. So dy dx at x equals to 1.6. This is the same table, so the spacing remains the same 0.1. And what would be our backward y power n? Backward yn.
(0.281).
Yeah, 0.281. So you replace this as 0.281, then plus a half. Then this second backward, when you read from the table, is minus
0.018.
18 plus a third into
0.005.
0.005, then plus a quarter into
0.002.
0.002, then plus a fifth into
0.003.
0.003, then lastly plus a sixth into
0.002.
Correct. So that's what you have. Then when you simplify, confirm that you'll get a number close to this, 2.75. Then lastly, the second derivative for this problem. By definition, the second derivative at x equals to x naught is 1 over h squared into backward squared yn plus backward power 3yn plus 11 over 12 backward power 4yn plus 5 over 6 backward power 5yn, then plus 137 for 180 backward power 6yn plus other several terms. But we know our table can allow us to reach up to the sixth difference. So this just with our last term.
Excuse me, sir.
So yes.
The h is it not supposed to be 0.6?
For this table,
Yes.
remember
Or
h.
1.6.
Remember h is given by h means mesh spacing or interval of differencing is a distance between consecutive values of x values. So you see in our table, we were having x, we have 1, 1.1, 1.2, 1.3, 1.4, 1.5, 1.6. So what we normally call h is the distance between two corresponding values of x following each other. So the same as 1.2 1 minus 1.0, or 1.2 minus 1.1, or 1.3 minus 1.2, or 1.4 minus 1.3, or 1.5 minus 1.4, or 1.6 minus 1.5. So just get the distance between corresponding values of x following each other is what defines the h. Distance between values of x following each other, and it's actually uniform for all. So,
Yes, thank you.
yeah, so when you are having the same table like this table, whether you are using the Newton forward or Newton backward formulas, h remains the same.
Thank you.
So it's, yeah, 0.1. So we'll have d squared y dx squared at x equals to 1.6 will be 1 over 0.1 square into the second. Now from our difference table, the second backward of yn. Negative 0.018, then plus 0.005 plus 11 over 12 into 0.002, then plus 5 over 6 into 0.003 plus 137 over 180 into 0.002. And if you work out this, check that the answer is roughly negative 0.715.
44.
Yeah, so, okay, maybe, yeah, it might be correct. If you write all the, in fact, I'll advise you to write all the digits without rounding off. So write the whole answer the way the screen of your calculator is displaying. These are a rounding off solution. So that's what we have. So I'm giving you powers to go and read on other numerical differentiation methods based on other formulas, having give you the kickstart. So I give 5 minutes break and then we come back to finish on numerical integration. So we resume after 5 minutes.